and that right there, I just realized, says arithmetic, which is wrong. Let me fix that right now. So that where it says number 13 should say geometric. I copied and pasted that and didn't. It's there. And okay, so let's look at 14 here. It says, what is the common ratio for the sequence above? So for 100, 102, 104.04, 106.121208, we need to know the common ratio. What are they multiplying by there? I can kind of tell that it is multiplying because it's like from 100 to 2, that would be adding 2. But you definitely don't add 2 to get to 104.04, right? So it has to be some sort of multiplying because it's not a constant value that's being added there. What do you guys think? Yes, it's going to have to be like a 1 and a decimal. Is 1.02. Very good. The easiest way to come up with this, especially if it's a difficult one that you don't really see there, is to take a term, any term. It just can't be the first term because the first term doesn't have a previous term. Take any term, 102, divide it by the term that comes in front of it. Whenever we were doing arithmetic sequences, we subtracted it. We did the term minus the one before it. But with geometric, you want to divide. It's called the common ratio. Ratio is division, right? So that gives you 1.02. It will work even if you use other numbers. So if you do 104.04 and you divide it by 102, that obviously would be one you're probably going to need a calculator for, but you will get 1.02 again. Okay, so the common ratio, we usually use an R for that, would be 1.02 for that. Seems sort of like a weird one, but it's really not for these scenarios because this is what you're going to use whenever you have, like, for example, like compound interest, right? So if you had an interest rate of 2% on something, like if your savings account had an interest rate of 2%, this is what you would do. You would multiply by 1.02. So that sort of stuff does show up in real life pretty often. Okay, questions on 14? All right, 15 asks us to write an equation for the sequence shown above. So in this case, I've got 2, 6, 18, 54. Common ratio is a little easier to find here. What's the common ratio? 3. You are multiplying by 3, right, each time. So you here would multiply by 3, and then multiply by 3, and then multiply by 3. So what I need is an equation, a sub n equals something where, like, if I plug in for my n, if I plug in 0, I should get 2. If I plug in 1, I should get 6. If I plug in 2, I should get 18. Right? So, anybody know what it could be there? What? Oh, I'm sorry. They do use a G. Let's use a G. Sometimes they'll use an A no matter what. A lot of the notes that Mr. Passwater had used a G whenever it was geometric. It does not necessarily have to be an A or a G. It really could be any letter. It could be like R or Z or something. But it'll have that little sub N. Technically, I guess I could use a letter other than N as well for that, but it would have a subscript for sure. But we do use a G here, so let's change that. All right, what do you guys think? 2 parentheses 3. Okay, to the power of n. Okay, let's think about it, see if it works. 2 times 3 to the 0 power. 3 to the 0 power would be 1. 2 times 1 would give you 2. That works. 2 times 3 to the first power is just 2 times 3. That's 6. That works. 2 times 3 to the second power would be 2 times 9, which is 18. That works. That's very good. So notice down here we've got, this may have been sort of where Peyton was looking. Did that help you, the formula there, or did you just think of it? Other equation in the table that you look back at? Good. He was kind of taken from the one that we did before to see that this number right here was like the starting number, right? And that G sub 0 right there, that's what that means. That means the starting number right there, or your initial value. So that starting number is right here, and then R, that right there, is your common ratio. And it will make an exponential equation there. Whenever and we're going to study exponential equations more in this unit, but whenever you learned about exponential equations, it was A times B to the X power. A was that starting value, B was that growth or decay factor, and then your X was usually time when you were doing applications. This is similar here. Okay, questions? All right, I've got another question for you that I want you to try here. The fifth term of a geometric sequence is 12. So that's telling us A sub 5 is 12. And the fourth term is 6. So A sub 4 is 6. Oh, I'm just in the habit of using A. You can use either one. It really does not affect the notes for this that Mr. Passwater put together. He used a G anytime it was geometric. You do not necessarily have to do that, and in my old regular pre-cal days, I never did that, so that is probably why I keep using the A instead. I just always use the A for everything. Either one is fine. Yeah, they will probably either use A's for arithmetic, G's for geometric, or they might use just like A's for everything. I think it's kind of unlikely that they'll use G's for arithmetic. They could also just use a completely different letter. They could call it like C sub N or something. So the letters don't have to be specific things necessarily. Mr. Passwater did use G's for all of his geometric sort of to distinguish here. If they just asked you to write, like if it was an open-ended question and they just asked you to write an equation, and they didn't specify write an equation G sub N, you could use any letter that you wanted there. It's probably not a bad idea to use a G here to remind yourself of what's going on. I've just, in honors pre-calculus, I taught this in a lot more depth, and I never did that, so I've just got a habit that's hard to break for that. So, but either one could be okay. The question's asking you for the 10th term. So I want you guys to find that for me. You can do it however you want. Find that 10th term for me. I'm going to let you try it on your own first. There's several ways you could approach this. Doing like this, first of all, I wrote this a little bit backwards. What are you multiplying by? Because you're multiplying by 2. So I saw several of you just doing, well then G6 would have to be 24. G7 would have to be 48. G8 would have to be 96. G9 would have to be, what do you get on that one? 192, and then that makes G10, twice that, which is 384. All right, definitely works to do that. The only problem is sometimes they might ask us a number that's a lot larger than that, where it would take a really long time. So did anybody do this without just looking at each term? Did anybody do it differently? What'd you do, Reese? Okay, what'd you get for your function? Okay. How'd you get that 3/8? Right. Okay. So that would be, this next one would be 3/2, and then G1 would be 3/4, and then G sub 0 would be 3/8. Right, and then so you could write 3/8 times 2 to the n. That would definitely work. Okay, and then you just plug in 10 to that. Yes. As long as you don't round anything off. If you round anything off, it will give you increasingly inaccurate answers as those exponents get larger. Exponentials are really dangerous for rounding because you might round, like you might be like to the 5th decimal place correct here. But whenever you start raising it to exponential powers, your error raises exponentially as well. So just make sure you don't have to round anything. But that one you can get a pretty easy, like 3-digit decimal for that, so it's fine. Anybody do anything different? I think that yesterday we did this one this way, and it kind of made you not want to do this other method. What if I did this? Like, what I'm doing right here is I've got the 5th term, right? And it is 12. And so I'm having to multiply by 2 to get the next term. That gives me my 24, right? And I take that and I multiply it by 2 to get the 48. And then I multiply that by 2 to get the 96. And I multiply that by 2 to get the 192. And then I multiply by 2 one more time to get the 384. Which could be written like this. 12 times 2 to the 5th. Okay? Where would that 5 possibly come from? Like 10 minus 5, right? So if we don't want to go all the way backwards, because especially on this one, going backwards to 0 starts getting you into a bunch of fractions that you'd maybe rather not deal with. We could use this formula that they have down here, where we just take the term that we know, G sub k, so this is a term we know, and then for our exponent, we do n minus whatever term that is. So like for this one, G sub 10 would be the term that we know, which is 12, times common ratio, which is 2, to the 10 minus 5 power. So we're starting at the 5th term, so we got to subtract 5 from that number of times that we multiply, and this would also give you the 384. So this is a lot like what you saw on that homework with the arithmetic formula. It's just an exponential version of that, right? So if you want to start at a term that's different from what you, like at the term that you know, then you just need to subtract that term from the k, or subtract that term from the n right there. Okay, questions? If you get this, like if you get a question like number 16, any of these are valid ways to solve it. So, you know, you can do any of these to solve the problem. Okay, let's look at a few multiple choice questions that you might see to give you an idea of like how this stuff may be asked on my test or the AP exam or something like that. So consecutive terms of a sequence have the value 10, -5, 5 halves, and negative 5/4 of the following which describes the sequence. Okay? So I've got my options look like most of them say this is geometric, but the last one say the terms are part of a sequence other than a geometric sequence because the common ratio of a geometric sequence must be positive. Have we heard that anywhere? This is the terms of a geometric sequence must be positive. No, that one's not going to be it. So all my options are geometric. I'm multiplying by something. What number would I be multiplying by here to get from 10 to negative 5? It is negative 1/2. It also is like you're dividing by negative 2, but that common ratio is the number you're multiplying by. So if it looks like you're dividing, then you need to change that to a fraction and multiply instead. So B would be your answer for this one. All right. Correct. Correct. So if it looks like subtraction, add a negative number. Right. For example, on number 18, I've got 8, 5, 3, negative 1. Okay. I've got options of arithmetic or geometric here. What are we doing? Are we adding or are we multiplying here? Is adding. What are we adding? Negative 3. So you are adding negative 3 each time. So that makes it arithmetic. So B and D are not correct. And then it says the terms could be a part of an arithmetic sequence with a common difference of negative 3. And the terms could be part of an arithmetic sequence with a common ratio of negative 3. Which one of those is correct? It's the difference. It's A. That's almost like a vocabulary question that they've worked in there because the number itself, there's no like differences there. It's almost a vocabulary question. All right, let's keep going. For 19, the general term of a sequence is given by a sub n equals 25 plus 2n minus 5, where a sub 0 is the initial value. Which of the following expressions also gives the general term of the sequence? All right. Any of these options you think we should probably go ahead and rule out? Okay. A feels wrong for sure because I don't know how we just like jumble all the numbers up and still get the same answer. It feels wrong. I wouldn't be as quick to throw it out. I would definitely throw out D. Why is D a bad choice? It's raised to a power. It's exponential. This one is not raised to a power. This is an arithmetic sequence right here, although it doesn't tell us whenever it's just sort of like a linear function. What do you guys think we could do? Let's distribute that too, because it works just like equations of lines. So a sub n equals 25 plus 2n minus 10. And that's going to be a sub n equals 2n plus 15. If we combine those, so it's going to be B for that. A is just a distractor where they've jumbled the numbers up, trying to make you think it's harder than it really is for that. Okay, questions? Okay, I put this on here. I do not like it whenever they do this, although I saw this on like a topic question on AP Classroom. So I don't like whenever they do this. I'm not going to do it to you, but I'm not certain that they will not do it to you on the AP exam. They might do this to you on the AP exam. First term of an arithmetic sequence is 6. The common difference is 3. What is the seventh term of the sequence? Okay. You figure it out on your own first. Try it on your own. I want to see what we get as the answer on our own. It's not a particularly difficult problem. There's just one little tricky thing that I feel like kids are going to get wrong a lot. Hold on. I may have the answer choices wrong. I think I've got the answer choices wrong.
Did you mean to do like arithmetic, or did you want to do geometric? Okay, geometric. But that one, but the arithmetic does not for this one.
Yeah, I think I've got my answer choices wrong. Or I meant it to be geometric. Who knows which one? Let's, let me change my answer choices. Let's make this 24 and 27. Okay. Now see what you get. I'm thinking my answer choices were just wrong. Surely I wouldn't have done arithmetic and common difference and actually meant to do it geometrically. Okay, what are you guys getting? A? How about B? How many of you got A? How many of you got B? Okay. Anybody got C? Or D? Okay, C and D are definitely not it, because C and D are the answers that you might would get with a geometric. So those are definitely not it. We are getting, some of us are getting A, some are getting B. And I do not like this problem because I think the reason that we're getting different answers is because of the way you're interpreting this first part. So the first term of an arithmetic sequence is 6, should be A sub 1 equals 6. But did some of you do A sub 0 equals 6? Like your 0 was 6. So it is supposed to be A sub 1 equals 6. A sub 0 is called your initial term, which is different from your first term. But initial term and first term sound too much the same to me. So I might give you the same problem, but if I put first term, I'll put A sub 1 in parentheses out there beside it to remind you that it is not the 0 term for that.
If they wanted us to start at 0 and they did something like this, would they say the starting term instead?
They probably use the word initial is what I think that you would see as well. I hope they don't do it to you because I feel like it's a little misleading. Like, it's fine as long as they put the little A sub 1 or A sub 0 behind it. That clarifies what they're talking about. First and initial sound too much the same. But I believe whenever they do this, they are telling you A sub 1. So then you've got a couple options on how to deal with it. If you want to use the shortcut, if you want to go straight to A sub 7, then you're starting at 6, and you're going to add 3, and you want the 7th term, so you would do 7 minus 1 right there. So 6 plus 3 times 6 is going to give you 6 plus 18, which is 24. You also could just do A sub 2 equals 9, A sub 3 equals 12, and so on, and you should also get it 24. But if you got 27, if you got B, You added 3 one too many times. Probably a good chance because you started thinking that was the 0 value instead of the first value. If I give it to you, I'll try to clarify. I don't know what they may do on the exam because there was an AP Classroom question that looked like this, which is the reason I threw it in here. All right, is that everything on this one? Yes. Okay. All right. Change in linear and exponential functions. So we are going to kind of relate what we've learned about sequences to their functions that go with them, and arithmetic sequences are going to behave like linear functions. So in an arithmetic sequence, a sub n is your nth term. A sub 0 is your initial term or initial value. And D is our common difference. And if we're writing an explicit equation for an arithmetic sequence, then we can write it a sub n equals a sub 0 plus common difference times n. There. A linear function is going to be very similar. The pieces are going to kind of line up. Whenever we're finding f of x, that's sort of like a general term that is going to be giving us sort of the y value at that point. So y value when x equals whatever number you've got. There. B, what is B on a graph of a linear function there? Is your y-intercept. And remember that at a y-intercept, x equals 0. So notice initial term, your n is 0. At a y-intercept, your x is 0. Those are related there. And what would we call the m? That is your slope, or we also like to call it the rate of change. There. So as you can see, the common difference is pretty much your slope or your rate of change right there when we're looking at these. Okay, questions on that? Moving on. Let's look at a couple other forms for this. So this was that shortcut formula that I was using on the answer key. It also is in those notes. It's a sub k plus d times n minus k. This is what we were using if we didn't have a sub 0. They gave us like a sub 10, right? So we would put that here, and then we would subtract 10 over here. So a sub n is still the nth term. A sub k is your kth term. That's the term that you know. So it'd be 12th term, yeah. There. And d is still your common difference. So this directly relates to the point slope form of a linear function. I do not think, I'm not sure if they teach you point slope in Math 1. I used to not teach point slope in Math 1. The reason I did not teach point slope in Math 1 is because my kids never memorized the stupid formula. And if you don't memorize the formula, then you can't use it. It's actually easier to use than the way that I do teach, but kids wouldn't memorize the formula, and so they wouldn't be able to do anything with it. I do really like that we're throwing this in here right now, because in calculus, I make you guys use this pretty much all the time, every time you write the equation of a line. The reason is because it is as long as you know the formula, and usually if you make it to calculus, you're a kid that can memorize a simple formula, then you don't like make mistakes quite as easily whenever you do it there. So this formula right here can be used to write the equation of the line when you have any point on the line, not just the y-intercept. So you guys remember y equals mx plus b usually pretty well. Does this look familiar? Have you seen it before? That won't surprise me if you have not. I think Hunter was actually doing this in Math 1 down there with Miss Ball the other day, which I don't see kids that have seen this till they get to me. But it's really pretty simple to use. F of x is still just your y value. X1, Y1 is any point on the graph. It's helpful to use this formula because it can be for any point on the graph. You don't have to have the y-intercept. It could be the y-intercept, but it doesn't have to be. And then m is still your slope. And like I said, this is called the point slope form of a line. So slope intercept is the one everybody always remembers. Y equals mx plus b. It's like the one thing kids remember from Math 1. Y equals mx plus b. That is called slope intercept because the m is your slope, the b is your y-intercept. This one is called point slope because to use it, you need any point on the graph and the slope for that.
And then, the x is just your x value, right?
Yeah, x is just your x value in that case. So it does not get replaced. So let's look at writing the equation of a line two different ways. Now this is Math 1 stuff right here, but we're going to need to use it in other things. So we are going to go over it. So when I teach this in Math 1, I use slope intercept form, which is y equals mx plus b. Okay, I teach it because nobody remembers the formula very well for the other. If you're going to do this with slope intercept form, it tells you your slope is 2. So you're going to put that right there for your slope. And then it gives you the point 4, -8. So this is your x coordinate and this is your y coordinate. Your goal next is to find that y-intercept. So you're going to plug in -8 equals 2 times 4 plus b. And then you're trying to solve for that b right there so that you can get the y-intercept, and then you'll have your slope and y-intercept and can write the equation of the line. So you're going to have to multiply those together. So you got -8 equals 8 plus b, and you would need to subtract 8 from both sides, so you get -16 equals b. And so then that needs to go back up here into this equation, and y equals 2x minus 16. I know it's been a while. Does that seem like probably what you learned to do? I know we have trended towards just doing that in the past many years. When I was in school, we always used point slope form. Y equals mx minus x1 plus y1. Notice it's a minus on the inside of the parentheses, but a plus on the outside of the parentheses. Don't think of it as it always has to be negative, always has to be positive. It's the opposite sign on the inside, same sign on the outside, which kind of mirrors what we've talked about with transformations. Everything on the inside is backwards, right? Point slope form is helpful because if you know the form, all you've got to do is plug in x, we're going to call this now x1 and y1. So you're going to do y equals slope is 2. You leave the x there, it stays, minus x1, which is 4, plus y1, which is negative 8. Now, the reason that I make you guys do this when you get to calculus, because one of the things that we have to do in calculus is write the equation of a tangent line. So we do a lot of writing equations of lines. Is on the calculus exam, they don't care if you simplify. So you can leave the answer like that. And so it's one step and you're done on that. For us, they do have some things that we are required to simplify sometimes. If they tell you you have to simplify, it's very simple. You just distribute and you get y equals 2x minus 8 minus 8, which is also y equals 2x minus 16.
Is there any time you can cut you off for some fun?
Only if you simplify incorrectly. Yeah. If you simplify correctly and it's mathematically correct, you're fine. Now, if you had, like right here, said negative 8 minus 8 is 0, and you just got y equals 2x, then even though you were right above, you'd lose points on that. Okay? Questions there? All right, let's talk about geometric sequences for a minute. So for your geometric sequences, g sub n is your nth term. G sub 0 is your initial term or your starting term. And R is your common ratio. Okay. This directly relates to exponential equations, which we'll get into even more on Monday. But you've seen it before. Again, this is really technically some Math 1 stuff here, although it shows back up in 3 as well. F of x is your y value of the function at that point. A is your initial or starting amount. Thank you, Autumn. And then B is your growth or decay factor. There. All right. So these things, you know, that growth or decay factor directly relates to that common ratio. Your initial term, your initial amount, those are directly related there. Let's think about this formula right here. Again, G sub n is your nth term. G sub k, what would that be? It'd be the term that you know, your kth term, which could be the second term or the 8th term or the 9th term, whatever they've given you, and R is still common ratio. You could also write this in sort of a point slope-ish sort of form. This would be your y value. X1, Y1 is any point on the graph of F. And B is still your growth or decay factor. Usually that's usually not. If it's like a word problem, it might be like your interest rate. And you'll have to figure out what it is or something like that. If it is a geometric sequence, they'll usually call it the common ratio. Yeah. For linear functions, this is a phrase that they like to use in the AP stuff, and we've seen it already before. Over equal length input value intervals, the output values change at a constant rate. We saw this a lot when we were looking at tables. Equal length input value intervals means you're going up by the same number for your x's, right? And then your y values are going to change at a constant rate. the change M in Y is based on, oh gosh, what's supposed to go there? Slope, addition. See my trick there? I put the right word and I make it white so it shows up whenever I forget it and need to go look at it. Because sometimes, like, the word slope would not have been a terrible word to fill that in with. Addition. There. Your whatever your common ratio would be, or your rate of change would be. All right. Now, over equal length input value intervals, the output values change blank right here. So if I'm looking at exponential, think about a table for this. Like an x, y, like I got 0 is 1, I got 1 is 3, I got 2 is 9, I got 3 is 27. So what's happening here is this goes up by 2, this goes up by 6, this goes up by 18, right? And if I do it again, this goes up by 4, this goes up by 12, right there. So what's going to happen here, you don't ever get like the same number with quadratics or cubics or quartics. You would eventually get the same number. These output values change proportionately. And the change is based on multiplication. Okay. Here at the bottom, if you have 2 points, you can write the equation of a linear function, exponential function, arithmetic sequence, or geometric. That's all you need is 2 points to be able to write these. You would need to know which type you're dealing with here, but all you need is 2 points. So we're going to do these and then we'll quit. So first thing we got to check here is that we've got equal length input values. So are all of these going up by consistent numbers? Right? They're not the same, but like we're going up by 3 on that first one, 1 on the second one, 2 on the third one, 5 on the last one. We're not going up by like 1 here and then 2 here and then 7 here. So we can just look at this side. So this one goes down 2, down 2, down 2, down 2. What have we got right here? Linear, exponential, or neither? Linear. Get the same number, it's linear. Alright, right here, goes up by 1, goes up by 3, goes up by 5, goes up by 7. Okay, definitely not linear. Is it going to be exponential? To see if it's exponential, do the next one. How much does this go by? 2, 2, 2. This is not exponential. Exponential, that will never happen. What is this one? This one's quadratic. So I put neither. But if you want to, you could put quadratic there in parentheses. Okay. If we look at 4, we go by 1, 2, 4, 8. Now, I see a pattern in that. I'm still multiplying by 2, right? Even in my rates of change. Like if I keep going, 1, 2, 4. I'm seeing that pattern like it's still multiplied by 4, right? This is what exponential looks like. Right? And it's being multiplied by 2.
So even though like the x values are going up by 2 as well, like it doesn't matter. Like it would.
The x values, yeah, but as long as they are equal lengths, like you're not like you're going up by 2 each time or 1. It couldn't be like 0, 1, 7, 10, 15. Then you can just look at the x values. And so for that last one, what's happening there? It's also going to be exponential because you are multiplying by 1/2 for that one. So that one would be exponential. We didn't get that very last one, but we almost got done.